Now let's use the Pythagorean Theorem to find x. We know a squared plus b squared is equal to c squared. So for us, we're going to say 3 squared plus x squared is 8 squared. So 9 plus x squared is equal to 64, and x squared is going to equal 55. Well, we're not interested in x squared, we're interested in x itself, which ends up being the square root of 55 that cannot be simplified. Now, this is not going to help you if you're a carpenter and you're trying to find out how long this side should be. You'd actually have to take the square root and find out that this is somewhere between 7 and 8 to get some specific values. But in mathematics, we're going to leave this in its simplified form. We don't want to go with decimals. I put number 11 on here specifically because people make mistakes. People say, ooh, let's square root the a squared, let's square root the b squared, and let's make the answer a plus b. Do not do that. This right here cannot be simplified. Now let's talk about why that cannot be simplified. If I were to write this instead as a squared plus b squared all to the 1/2, because that's what a square root is, we would not be able to apply that 1/2 power to what's inside because there's a binomial, there's two terms inside. And you know that you cannot square root across a plus sign. Therefore, you can't do it here also. So this is a cannot be simplified type of problem. Now that same idea shows up in this next problem. You cannot square root across these plus signs. However, if you instead write this as x plus 2 quantity squared that you're square rooting, then you can say, aha, out comes x plus 2. But there's a catch. You need to have absolute values around the entire x plus 2 here, because you know that the square root of something squared is equal to the absolute value of that something coming out. Now let me pay attention to something else here. I know we don't want to use absolute values on anything we don't have to. If you were to write absolute value of x plus 2, that is not the same as what we have above here. You do need the whole x plus 2 inside the absolute values. And I can still illustrate that easily by giving you a counter example. Let's substitute in a negative number like -6. If you substitute -6 into x plus 2, all absolute values, you get -6 plus 2, which is -4. The absolute values becomes +4. If you stick -6 into what I've just crossed off, you end up getting 6 plus 2, which is 8, and 8 and 4 are not equal to each other. So leave the absolute values around the entire sum x plus 2. For this next problem, we have a negative inside of a cube root, so we know that our answer will be negative, but we've got to break down this 192, which is a little bit large for us. That'll be 2 times 96. 96 can be broken down into 6 times 16. I'm going to bring down my 2 and my 3. I'm going to have a pair of 4s coming down with a 16. So 2, 2, 3. Couple more 2's, and then a couple more 2's again, and I'm looking for 3 of a kinds, and I've got one 3 of a kind with these 3 2's, and I've got another 3 of a kind with those 3 2's. So altogether I've got a 2 times 2 coming out with the negative, so we'll have a -4 on the outside, leave a little space, we'll have a cube root of the 3 left over, and don't forget that index there. Now let's move on to the variables. We're dividing each by the exponents by 3. So 6 divided by 3 is equal to 2 on the a's. 1 divided by 3, it's not going to go in at all, just 0, remainder 1. And 2 divided by 3 goes in 0 times remainder 2. So basically all that can come out is a squared, and we're going to have to leave the b and c squared inside the cube root. For number 14, we can break down this 18. I'm going to do this with a sideways factor tree. That gives me 6 times 3. My 6 can become 2 times 3 with a 3 I've brought down. And this is a square root, so I'm looking for a pair of 3's. So what do I have now? My numerator is 7 times 3 root 2. I could have made that 21, but I wanted to, for effect, show you that this 3 will cancel with the 9. Give me 1 and 3 there. And this will finally reduce to 7 root 2 over 3. In number 15, we're taking the cube root. Now, it's tempting to take the cube root directly, but do you notice how inside this radical you can reduce? As long as both terms are inside, you can reduce this, and I can rewrite this problem as the cube root of negative 27a to the third over 8. Now, it turns out that everything is a cube right there, so we'll just have negative 3, which is the cube root of 27, a over 2, which is the cube root of 8. Okay, I do not want to take 7 to the 5th power for this problem, so I'm going to have to treat this a little bit differently. I'm going to think of this as 7 times 7 times 7 times 7 times 7. Here's a pair of 7s, there's a pair of 7s, so I know I'm going to have 49 on the outside of my answer with another 7 left over inside. Each of these exponents is going to get divided by 2, and so I'm going to leave myself a little space here, put the 7 inside, and let's start with u to the 12th. 12 divided by 2 is 6, so I'm going to have u to the 6th on the outside. V to the 20th. 20 divided by 2 is 10, so I'm going to have v to the 10th. W to the 65th. Well, 65 divided by 2 is going to not go in evenly, but 64 does, so I would have w to the 32nd with one w left over inside. And with the x's, 80 can cut in half quickly, and we would have x to the 40th. And I didn't do a super good job of leaving a lot of space, but you can see what the answer is. We have another Pythagorean theorem problem, but this time the x is on the hypotenuse. So we've got 6 squared plus 12 squared is equal to x squared. That is 36 plus 144 is x squared, and that becomes 180 is x squared. Now we need to break down that 180, and I'll use a sideways factor tree here. This happens to be 36 times 5, and so if I square root both sides of this equation, I get x is equal to 6 root 5. Now I mentioned square rooting both sides of the equation. Technically, when you square root both sides of the equation, you need a plus or minus on the other side, but we know from the geometrical context here that we're dealing with lengths, and lengths must be positive, so we don't have to worry about that plus or minus.